Hello, welcome back to the online tutorial on quantum chemistry. Today we will begin our journey through the historical events that led to the development of quantum mechanics. Today we will learn how classical mechanics was not able to explain blackbody radiation. We know that any solid will emit radiative energy at any temperature due to the vibrations of its particles. Even human body gives off infrared radiation, but the amount of radiation is very small. If the solid is heated, it will emit radiation of high frequencies at higher intensities. And we know that when a burner of a stove is turned on, first it will be dull red. When it is heated further, it will become bright red. And if the temperature is increased further, it will appear as white and then blue. In terms of frequency, as the temperature of the burner is increased, it comes from a low frequency region, that is a red region, to a high frequency region, that is a blue region. In fact, the exact frequency spectrum of any radiating material will depend on the nature of the material itself. But if a body can absorb and emit radiations of all frequencies, then such a body is called a blackbody. And the radiation emitted by the blackbody is called blackbody radiation. A close approach to a blackbody is a hollow enclosure with a small hole in it. This is a hollow enclosure. This is hollow enclosure with a small hole here. The radiation entering through this hole undergoes continuous or repeated reflections. If it enters here, it undergoes repeated reflections inside this cavity. And due to these repeated reflections, the radiation will be completely absorbed. And by definition, blackbody absorbs all radiations falling on it. So this can be considered as a perfect blackbody. And when the inner surface of this hollow enclosure is heated, it will start to emit radiation. And the radiation coming out through this hole can be considered as blackbody radiation. Now, let's have a look at the plot of the intensity versus frequency of the blackbody radiation. I am taking intensity I in this axis and frequency nu in this axis. This is a plot of the intensity versus frequency for a particular temperature T1. This is for the temperature T1. Here we can see that for low frequencies, the intensity is small. As the frequency is increased, the intensity also is increasing. And for a particular frequency nu1, the intensity reaches a maximum, and then for higher frequencies the intensity decreases. Now, this is the plot of intensity versus frequency for another temperature T2, where T2 is greater than T1. And this is the frequency nu2, which is corresponding to the highest intensity or maximum intensity. And we can see that nu2 is greater than nu1. And for another temperature T3, this is the plot. and this is the maximum intensity, and this maximum intensity is corresponding to the frequency nu3. And we can see that as the temperature is increased, the intensity maxima are shifting from a low frequency region to a higher frequency region, from low frequency nu1 through nu2 to a high frequency region nu3. So this is the plot of the blackbody radiation at different temperatures. Scientists of the 19th century were all trying to derive an expression for the experimental blackbody curves, but all of them were unsuccessful. One of the most noted expression was by Rayleigh and Jeans, and it is called Rayleigh-Jeans law. Rayleigh-Jeans law. And according to Rayleigh-Jeans law, rho nu T d nu is equal to 8 pi kBt by c cube times nu square d nu, where rho nu T d nu, this is the density of the radiative energy, density of radiative energy between the frequencies nu and nu plus d nu at the temperature T. And Kb, this is the Boltzmann constant, the value of which is 1.38 times 10 raised to minus 23 joules per Kelvin, and c is the velocity of light, which is equal to 2.99 times 10 raised to 8 meter per second. And if we are plotting the intensity versus frequency from Rayleigh-Jeans law, the plot will be like this dotted line. Here we can see that this Rayleigh-Jeans law, the plot from the Rayleigh-Jeans law is fitting to the experimental blackbody curves at a low frequency region. But if the frequency is increased, this diverges as nu square. And this divergence at a high frequency is called ultraviolet catastrophe. Here we have a phenomenon that classical mechanics was not able to explain. So the assumptions of classical mechanics were insufficient to explain some physical phenomena. So new assumptions are to be made. In fact, it was a German physicist, Max Planck, who brought a revolutionary assumption in order to explain experimental blackbody curves. And this revolutionary assumption led to the development of quantum mechanics. That we will learn in the next class in detail.